I'm a deep learning solution architect. Effectively, I work with customers to try to help them deliver their echo, no problem. So I help them deliver their projects. I'm an interface between them and our engineering teams, making sure that we are all progressing in the direction we want to. And before I start talking about perception algorithms and self-driving cars, I want to set up a bit of context, because not everyone knows who NVIDIA is and why are we talking about self-driving cars in the first place. A lot of you might know us because of our gaming heritage. Effectively, we're a company that manufactures accelerators for computer games, and a lot of you or your children will use our products on a day-to-day basis to play Battlefield, Tomb Raider. But it turns out, and we figured it out more than a decade ago, that exactly the same functionality that is required to accelerate computer games can be used for a very wide range of other applications, because that functionality is linear algebra. Yes? So in order to be good at rendering games, you need to be really good at matrix multiplication, and a lot of problems in our day-to-day life are actually built with math. And we came to that realization, as I've mentioned, more than a decade ago, and since then we've been investing heavily in high-performance computing. Yes? And at this point of time, we are powering overwhelming majority of the world's most powerful supercomputing clusters, including this system here, which is Summit. At this point of time, world's most powerful supercomputer, and that system has 27,000 of our GPUs. So our systems for more than a decade are used to do things such as model weather, yes, model seismic properties of the earth, to find oil fields or model earthquakes. They are used to model airflow around objects that you use on a day-to-day basis, such as cars, planes, etc., etc. They're used to build new materials, find new medicine. So GPU is already at the heart of a lot of scientific research, effectively, and is fairly universally present across supercomputing data centers across the planet. But also quite some time ago, we've noticed that also exactly the same functionality that allows us to accelerate science and allows us to accelerate games is effectively the foundation for machine learning, because those are very large optimization problems, and it turns out that our hardware excels in those problems. And it so happens that very large proportion of machine learning today is accelerated already by GPUs. And so whenever you go to Microsoft Search, to Bing, and you type in a query, that query goes through a huge number of different neural networks, and all of those are GPU accelerated in one form or another. Or whenever you go to Netflix, you watch a movie, you get a recommendation back, that's already executed via a neural network, and that neural network is executed on a GPU. But we've also noticed that you need that computational power not only in a data center, because not all of the problems can be solved like that, but there is a need to shrink that functionality. And this is what we've been effectively doing. Over the last few years, we've been working on shrinking that computational power to the form factor that can be deployed not only to vehicles, so self-driving cars, and this will be the focal point of our talk today, but also to a wide range of other robotic systems. So we've been working to shrink that HPC capability to a form factor where it can be deployed to those environments. And in fact, that's something that we already have. We have a mature end-to-end system for autonomous vehicles, including in-vehicle hardware and software that I'll focus on in a second. Obviously including the data center infrastructure required to build those machine learning models, but also in infrastructure and software to aid with tests of software and tests of integration between software and hardware. So in terms of the in-vehicle infrastructure, we have right now a fairly mature end-to-end and open platform for a self-driving vehicle. It's an end-to-end platform because it not only includes the hardware itself, because hardware without software is fairly useless, but it also contains an entire stack of software products that allow people to build their self-driving vehicle solutions, including components such as Drive OS, so the system that actually allows you to integrate all of the sensors within the vehicle and provide the basic functionality that creates the entire functionality of the car. But also software components, so models, perception models, that will be the focal point of the stock. Importantly, the perception is not only focused on what is happening outside of the car, but a large part of what we are doing is also focusing on what is happening inside of the car. Because you need to be aware not only of the surrounding, so whether there are pedestrians on your route or not, but also of the interior of the vehicle, whether you can actually safely give back control to the driver, whether the driver is able to regain control of the vehicle. We now have 370 plus partners that are developing their self-driving car solutions on that platform. This includes companies such as Volkswagen, Mercedes-Benz, Volvo, Audi, but also mobility service providers, so companies such as Uber, or if you know Russian market, Yandex, companies local to the UK, so 5AI, but also a large proportion of truck manufacturers, so Volvo, MAN, Scania, DAF, but also their supply chain. So companies that develop systems that then get integrated into the vehicle. So companies such as Continental, Bosch, Veoneer, ZF, a wide range of mapping providers, and specialty companies. So companies that look at their own dedicated autonomous solutions, such as Deutsche Post, looking at the last mile delivery. Yeah, so we have 370 plus adapters of this platform already, and people have been progressing, developing their solutions for a while now. And I guess the appeal of this platform is not only the fact that it's end-to-end, but also the fact that it's open. Yes, the users can choose to use any level of that stack they want, so they can choose only to use the hardware and build everything on top of that by themselves, or they can choose individual components as they wish. And indeed, that's exactly what we see. We've seen almost every linear combination of those elements used and developed by our partners. So yes, 370 users, but that's not everything. We've noticed that the world is not exclusively built of self-driving vehicles. So what we've done then, we've continued to shrink that functionality, and we have a series of even smaller and less power-consuming devices within the Jetson family, and a similar software stack for building robotics and autonomous machine applications. And again, this is a fairly mature platform with more than 200,000 developers worldwide and quite a few existing, quite successful industrial projects. So things such as industrial robotics, aerospace defense, healthcare, construction, agriculture. We see robotic applications in all of those areas. And what I'll be talking about today is our effort to build, especially this part of the stack. In this case, this part of the stack. So our effort focused on building perception algorithms. So algorithms that perceive the world around them, so perceive pedestrians in front of the vehicle, perceive obstacles in front of the vehicle, perceive the status of the driver, and the challenges related to that. Before,
can we just?
Yep.
A while ago, you mentioned power consumption. You mentioned the difference in these two platforms.
Indeed.
I think did you say 15 watts for the?
So the smallest one will operate with as little as 5 watts, I think, of electricity.
Right. And what is typical for a vehicle?
That depends on how the customers design that system. That's extremely specific to their camera setup and the algorithm selection.
But
So.
Hundreds of watts, or?
Yeah, something like that.
Yeah. Okay, thank you.
But not substantially more, because you have constrained power budget as well. So before I dive into specifics of perception algorithms, let's talk about just deep learning algorithms, because you need to come to a realization that what we're referring to as deep learning, it's not a new algorithm. These are just normal neural networks. In fact, there is nothing new about them. Yes, the algorithms that we are using today to build the self-driving vehicles of the futures are exactly the same as those that we used in the 80s. Yes, and the optimization approaches that we use today are exactly the same as we used in the 80s. Moreover, it's a trivial algorithm. You just take a bunch of numbers, you multiply them by a bunch of weights, you add them up, you apply usually a fairly trivial nonlinearity, you sum them up, stack them, and use very simple optimization algorithm, stochastic gradient descent, to optimize them. So you should be asking yourself a question: why didn't we use those models in the 80s, or at least why didn't we use them successfully in the 80s and 90s? Why is it only today that we are talking about self-driving cars and robotic applications like that? And in order to explain that and then explain to you complexity of building those systems, let me introduce this oversimplified graph that depicts a fairly universal relationship across the entire machine learning. So this relationship is the relationship between the amount of data that you provide to a model for training and model performance measured in some form of accuracy. It doesn't matter what the metric is. And that relationship is universal. It applies to every single machine learning model, irrespectively whether it's a large neural network or something as simple as linear regression. Initially, as you provide the model with some data, its performance will increase fairly dramatically, but then it will unavoidably plateau. So you will stop benefiting from the increased amount of data. And so that's a fairly brutal relationship, because it means that, if your product requires that much performance, you cannot achieve that performance just by increasing the amount of data. You effectively need to invest engineering and research time in feature engineering. And indeed, literally every single artificial intelligence community was doing that systematically for the last 40 or so years. Paper after a paper, people were coming up with better representation of the world around us, so that the job of those models became easier and easier. And this is how we've been achieving our goals for quite a few decades now, actually. And in comparison to that, in the 90s, neural networks performed very badly. So they didn't work, especially in comparison to some of the more powerful algorithms introduced in the 90s. So an algorithms such as support vector machines, small neural networks, they performed really, really badly. And that is why they were effectively not used. Their performance was so poor, in fact, that people stopped investigating them at some point in the 90s, almost altogether.
You said those were small networks.
Yep.
So can you quantify that? What sort of size are we talking about?
We will talk about it. Yep.
You're coming.
Yeah, I'm coming to that.
And is it possible to achieve 100% accuracy, or is that?
Yeah, I will come to that as well.
Okay, good.
Yeah, so you have to ask yourself a question of why. And if you understand why, everything else falls into a place, and it's easier to talk about so complex problems as the self-driving vehicle. And one of the most obvious reasons why they didn't work is just the observation that we did not have, neither could afford to have, data sets of the scale that we have right now. Storage was prohibitively expensive. How many of you had a 2 terabyte disk 20 years ago? It just was not possible. So we were forced to work with fairly tiny data sets. So this is a almost state-of-the-art data set in 1999. It's composed of 60,000 black and white images, 24 pixels wide, 24 pixels tall. Yeah. And even if we would have had those data sets, that would have been fairly useless, because we didn't have the corresponding compute to do anything meaningful with those larger data sets. Neither we could not have used larger models, because we physically did not have the compute to do so. And so, fortunately, and everyone knows that, we've been benefiting from the properties of the Moore's law. Yeah, so every year we saw 50% growth of compute, year over year. And that led to 1000x acceleration over every decade. Yes? And even though that now has come to an end, we cannot continue to scale single-threaded computing in the same way as we could. We can be smarter about the way we design compute. We can be smarter about the way we design accelerators, and companies like NVIDIA continue to grow their compute capability exponentially, even though it's difficult to do it just with Moore's law and Dennard scaling. Yep. And we know all of that, but it's easy to forget. It's easy to lose perspective. So the way I like to show people this graph is slightly in a different way. So this entire building in November 2009, so less than a decade ago, yes? We're 2019 now. So this entire building in November 2009, when working on one task, that entire building could deliver 1.759 petaflops, so floating point operations per second. Today, 2 petaflops can be delivered in a single device. Yes, at least from the perspective of deep neural network training. Moreover, half of this device, so 1 petaflops, can be rented on Amazon or Google for $20 per hour. Yep. And this is not a marketing slide. This visualizes a change in the paradigm, because suddenly the computing power that was reserved maybe to People's Republic of China, yes, United States of America, and maybe to a handful of labs, now can be rented on Amazon for 20 pounds, 17 quid. Yes. So that allowed people to do experiments. That allowed people to make mistakes. That allowed people to learn from those mistakes and iterate. Without that, it was not possible. So it allowed us to use larger data sets. It allowed us to use larger models. And suddenly, for no other reasons but that, those models that behaved really badly when the amount of data was small, not only started competing with what was then like 40 years of systematic research, but substantially exceed their capability. Moreover, as we've continued to grow the sizes of data sets and we started using even bigger networks, we've noticed that they do plateau, but they plateau in a totally different region than classical machine learning models. More importantly, we can move now this curve upwards just by increasing the size of the model. And this is effectively what happened in 2015. We saw networks like ResNet, where ResNet 50 has 60 million parameters. That's a large model. So think about linear equation. Y equals A of X plus B. A and B are parameters. This is an equation with 60 million of those parameters. You know, if every one of them is a 32-bit number, we're talking about 240 million bytes just to store that model, and say 200 megabytes, just the model itself. And to train that model once, so to make an experiment and fail to learn from it, that requires 7 exaflops of compute. In 2016, Baidu's deep speech, so a model that is very widely used in China to transcribe speech into text, had 300 million parameters and requires 20 exaflops to compute once. In 2017, Google Neural Machine Translation Model, so the model that you will use when you go to translate.google.com to translate a sentence from German to English, that has 8.7 billion parameters and requires 100 exaflops to compute once. So to conduct a single experiment and fail. And again, this is fairly meaningless, 8.7 billion parameter, 100 exaflops, but bear in mind, 100 exaflops is 2 years on a dual CPU server. Yeah, so you kick off the experiment now, you get results in 2 years' time. That's prohibitive. We could not have iterated or succeeded in those timescales. And it turns out that those models, when they are even larger and you give them even more data, they continue to improve. Yeah? But until late 2016, 2017, we did not fully appreciate the nature of that relationship. But we've started to see quite a lot of systematic research, especially 2017, beginning of 2018. And my favorite paper talking about this subject is by Baidu. Baidu is Google's direct competition in China. And what they've done, they've taken majority of the key artificial intelligence problems, so translation, language modeling, character language modeling, image classification, etc. And for every one of those problems, they've taken key neural networks that are used to tackle those problems. And for every one of those neural networks, across every one of those problems, they've trained those models with a varying amount of data. So they started with a small data set, they've calculated the error, they've increased the size of the data set, they've calculated the error, and plotted those curves. And what can you see? These are fairly straight lines. Yes. So for the first time in human history, we seem to have a promise of a tool that can achieve almost arbitrary performance, obviously up to some reasonable limits, so to the kind of base error if exposed to enough data. Yes? So, we can approximate almost an arbitrary function if we have enough training data set. And that's not something that we had. And that is why, people are so excited. That is why we fairly frequently hear about hype. But that's just the reality. We did not have a tool like that. And the properties of those tools are fairly important because suddenly we're transforming extremely complex problems into fairly easy problems. Yes? I mean, we see video analytics applications everywhere, sentiment analysis applications everywhere, chatbots. Those were prohibitively difficult problems a decade ago, all of them. And now they become trivial, yes? But more importantly, they transform unsolvable problems into expensive. And why expensive? Can anyone guess? It's expensive because of the logarithmic and a power law based relationship that we see here. So that means that if you have a problem that requires 80% say performance to solve, that will be trivial. But if you then need to increase that performance to 90%, you need exponentially more data. And if you need to increase that the performance from 90 to 99%, you need exponentially more data. If you need to increase performance from 99 to 99.9%, you need exponentially more data. So those unsolvable problems become really expensive. Yes. And what I'll do, I'm struggling. Okay.
Can you just define?
Let's just watch this and
Sure.
let's try to come back. Yes?
Can you define unsolvable problems in terms of compute complexity?
I'll show you.
You will, because you do
Yeah.
that.
Because now I'll boil down into automotive.
Yeah.
And that is a problem that I don't think anyone dreamed of solving like a decade ago.
Are you claiming that you can solve NP hard problems?
No. This is just a marketing slide. So we can solve really solvable problems, yes? But problems that are very, very difficult.
Yeah.
Yep. So what I'll show you is what we kind of mean by that. So I'll show you a short video. It's only like a minute long that summarizes the project that my wider team was working on. And I want you to focus on one thing when you watch that video. Try to think about what those problems have in common. Yes? Or I will not show you. Maybe I will. Here we go.
Exploring a universe of data to sharpen our view of the most distant galaxies. And studying black holes to help prove Einstein's theory of gravitational waves. I am a healer, giving doctors the power to turn mountains of data into life-saving breakthroughs. Identifying diseases like leukemia from a simple drop of blood. Even in our own homes. where
So what do they have in common?
Massive data sets.
Yeah, they are all supervised learning problems, yes? So they are all formulated as y equals f of x, where x is the data set that you have, y is the set of labels that you have, and f is the function that that neural network is trying to approximate. So if you're trying to build an image classification problem, so like that machine that was trying to identify the plants that you want versus the plants that you don't want, x is a set of images of plants, y is a set of labels, and the only thing that that neural network is doing is approximating that relationship. If you're building a system that translates German into English, x is a set of German sentences, y is a set of English sentences, and the only thing that that neural network is doing is approximating the function between them. Yes, if you're building a system that is trying to compose music, x will be a set of songs, y will be some subjective perception of beauty, and the only thing that that neural network will do is try to approximate that complex function. So that's a very powerful tool. With that formulation, you can solve really a lot of problems, yes? And that what gets people so excited. That is why we see companies such as Google, Microsoft, Apple, invest so much money into technology development, and governments appointing ministers of artificial intelligence, because we suddenly have a very complex tool. But that comes at a price, yes? And after all of that, I want to notice that, you know, when we've started working on perception algorithms quite several years ago, I think both us and the wider community underestimated the complexity of that problem. And building AI for self-driving cars is really hard. And the reason why it's hard is not because we don't know how to organize algorithms, because we do actually. The reason why it's hard is because that software stack, that end-to-end solution, needs to handle thousands of different conditions. Like, it needs to operate correctly at day, at night, during twilight, in presence or absence of lights, in presence of backlight, when the road is clear, when the road is crowded, when there is rain, when there is fog, when there is snow, and across thousands of geographical locations. Moreover, it's not a single neural network. In fact, we're building approximately 20 different models that all together form a solution that people will refer to as a self-driving car. So we have algorithms that do object detection, algorithms that do free space perception, algorithms that do distance perception, weather classification, lidar perception, scene perception, path perception, lidar localization, camera localization, mapping, and quite a few others, including ones that identify the state of the driver. So, and that problem becomes suddenly very complex, because not only they need to operate robustly across all of those different conditions, but more importantly, what do you need to do? You need to prove that they actually work robustly. And that task in itself is not easy. So as a consequence of that, this is actually our data collection schedule for this year. We are collecting really a lot of data. So right now we're sitting on 15 petabytes of hot data, so data that we use on a day-to-day to train and validate, and by quarter 3, beginning of quarter 4, we'll have approximately 180 petabytes of data that we are very actively using to develop and test those algorithms. As you need millions of real miles. More importantly, when your data set becomes so large, it actually becomes a fair challenge to do anything with it. So in order to say execute a test in a reasonable amount of time, and in this case we've defined reasonable amount of time as 24 hours, but it doesn't change much. So in order to conduct a single test on a data set of this size, you need 3,200 GPU nodes. Yep. So you need 3,200 computers to be all able to execute a single test once. And obviously, that's not enough. Yes, so and that has much more implications. So we don't even have such a large fleet. We have 30 cars with 12 cameras, radar, lidar, and we're collecting 1 petabyte of data a week. Obviously, not all of it is useful for training, because after a while of random data collection, your model already seen all of the normal day-to-day driving. And you're not really benefiting the model by recording the data at 30 frames per second either. So a lot of it can be discarded. That is why we're sitting on a 15 petabyte data set as a result of that data reduction. And you could say that a lot of companies have 15 petabytes large data sets. But this is a hot data set. That is the data set that is used all the time and needs to be close to the compute. But how do you get to 15 petabytes? Okay, it's fairly straightforward to derive randomly and collect 15 petabytes of data, but it needs to be, y equals f of x. We need the labels as well. And labeling 15 petabytes of data is non-trivial. That is why we hire 1.5 thousand people full-time labeling pavements, road signs, pedestrians, pushchairs, proms, bicycles, random objects on the street. So we have the capability to label approximately 20 million objects every month, and we do it across 20 unique models and 50 different labeling tasks. And to work with that, even the 15 petabytes, not to mention 180 that we're ramping towards, we have a 4,000 GPU cluster that is capable of delivering 500 petaflops of compute and 100 node large validation cluster. So cluster composed of systems that we used for testing. We have quite a few racks of compute. We have, in every rack, we'll have 1 petabyte of storage, and that's 1 petabyte of storage per 72 GPUs. Overall, about 30 petabytes provisioned. So you need to approach that problem somehow. And one of the first challenges that you'll hit is the fact that you need to do training on that data set. And you know that neural networks are large, but what you most likely don't know is that for any size of the data, it's always a good idea to make data look small by using a huge model. So, yes, so that is a problem. Fortunately, that relationship is not linear. Actually, for for the certain amount of data, you should be able to find the best model size quite easily, and it's not a linear relationship. That relationship plateaus quite quickly, and it's not just our subjective observation. There are actually empirical evidence showing that. So what you're seeing here is a relationship between model accuracy and mathematical complexity versus memory complexity of those models. So can see that you can choose a compromise. So as a developer, especially developer in such a complex application where non-functional requirements matter. So what I mean by non-functional requirements, it's useless to have the best in the world algorithm that does breaking if it takes 5 seconds to come to a decision, yes? And in those 5 seconds, the thing that you were trying to break will already be behind you. So you need to actually have something substantially quicker. So you're constrained not only in terms of your accuracy, but also your performance. But you can do that.
So
yeah.
This is saying that some models are too complex, too sophisticated
to meet those requirements.
To deliver useful results.
At least within the context of the hardware that we have today. And you have very clear budget of latency, yes? And that's not something that is negotiable.
And what sort of budget of latency?
That's vendor specific. That's very specific to how they've executed and designed their end-to-end system. That's not just a function of a model, that's a function of the entire system design. I cannot comment on that. But you can, if you do 60 miles per hour, you can figure out how much is acceptable.
You're talking about sub-second response.
Yeah, millisecond response, yes.
Right.
It's definitely, yes. In a second at 60 miles per hour, you will travel a fair distance, yes. And not to mention that that's just the neural network latency. The entire system has latencies. So we're talking about end-to-end system latency that needs to be reasonable. And that's a problem, because every sane team will need to iterate. So they'll need to have an idea. They'll need to have the option to translate that idea into some form of formal representation. In our case, since it's an advanced programming group, that's code, yes? Then you need to use that representation to experiment, typically fail to get new ideas. And only after you close that loop thousands and thousands of times, you get to a solution that kind of works. And only quite a few iterations later, you get to the solution that you can deploy. And that is a problem, because if you do just back of the envelope calculation, so say I have 100 cars, they generate 1 terabyte per hour, which is optimistic, because they generate more, and you collect for a working year, so 260 days, 8 hours a day, and you can throw away really a lot of the data, because as we said, it's redundant, you don't need all of the frames, and maybe you can even compress it, so you'll be able to compress it quite aggressively. You end up with 104 terabytes, and that's totally different order of magnitude than the one that I've just discussed. If you use one, that's an old GPU. We're already several families ahead, but if you use 1 Pascal GPU and a fairly complex neural network, to train that neural network once will take you 9 years. That's not a time in which you can do those cycles. If you take a simpler neural network, okay, it will take you 1 year, but then you do a bit of a sensitivity analysis, you adjust those numbers ever so slightly, and you end up with 42.6 years. And that's just a single experiment. Yep. So suddenly, it becomes, you have to ask yourself a question, initially you read papers, yes? You might even submit some papers, but if you cannot execute code, you cannot validate what you've done, how do you progress, yes? So as a company, we've been focusing on a couple of different things. First of all, how to make a single GPU as powerful as possible for this workload. And in fact, the difference in performance between Pascal and Volta architectures is 12x. So Volta generation GPUs are theoretically 12 times faster than Pascal. That's already something. But also we've been investing huge amount of effort into ability to scale linearly. Yes. So in the ability to take, say, one system and multiply it. So to rather than using a single system to train a neural network with 8 GPUs, to use 10 systems and to try to linearly decrease those training times. So what took I think 9 years with a single GPU, with 8 GPUs will take 160 days, and with 80 GPUs will take 16 days. And that in itself is non-trivial, to the extent where we had to develop our own communication bus that to large extent supersedes for those applications PCI Express, called NVLink, which operates at 300 gigabytes per second. Yes. We had to deliver our own switch technology that allows GPUs in a system similar to this to provide full bandwidth of communication between all of the GPUs in that system. Every one of those systems will have 4 or some of them even 8 InfiniBand connectors. And for those of you that don't know what InfiniBand is, it's a network technology that right now operates at a speed of 100 gigabits per second. And so you need to do really a lot of things to allow for that linear scalability. And actually, I think we've succeeded. So those systems are widely available through our partners and OEMs, so companies such as Dell, Hewlett-Packard. And we have very clear reference designs describing how to build systems like that. And in fact, systems like that are already available on Amazon Web Services and so on and so forth. We also built quite a few reference architectures discussing how to build data centers, so how to combine those systems into a larger, more coherent systems. And we've built a couple of those systems already. So our Saturn V, so the system that our perception team is using for training, is composed of 660 of those 8 GPU nodes. So 5,280 GPUs. And we've built much larger systems than that. So Summit is composed of 27,360 GPUs, and we've proven that we can train neural networks and scale that training on almost perfectly, almost linearly. And so I think we've achieved that goal. We can build extremely large systems that have a capability of scaling, and that's non-trivial. And I appreciate that not everyone will be able to build systems like that, but what we also see is that it is possible to reduce the training time. So ResNet 50, so neural network that I've mentioned earlier, in December 2015 would take 1,740 minutes to train once, and Sony, November 2018, demonstrated that they can train it on a very large system in 3.7 minutes, and I think last week Fujitsu demonstrated that they can train that neural network on even larger system in 76 seconds. Obviously, not everyone will be building large systems like that, and in a lot of cases it's not practical, but I think with a single system with 8 GPUs, you can get quite close to 180 minutes. And so you can do it in 3 hours. So, there are tools that even a small organization can deploy and use to solve smaller problems. So we've kind of addressed the problem of training of those neural networks, but how do we even prove that they operate? Now, if you think about it, people are really good at driving. And majority of events that you want to test against are extremely rare. Yes, so you cannot just collect 5 hours of driving and hope for the best. You actually need to put a substantial amount of effort to prove that you have done your job. So you have to have a fairly large scale training, validation approach that can test those algorithms across millions, if not billions of miles, across extremely diverse vehicle and world conditions. Yes. And moreover, you need a setup that is extremely repeatable and reproducible. You cannot just test on a road because, what happens if you change a single bit in that neural network? You need to start validating from scratch, yes? You've made a change, your previous results are void, are not valid. So you need something also that is reproducible. So you have a problem because, certain things you can validate using a software-in-the-loop approach. So perception algorithms, yes, you can definitely validate them fairly easily because they are provided with an image and they either perceive a pedestrian or don't. That's great. Some things you will have to test on the road because you cannot do it in any other way. Certain things need to be tested on the road, and that's great. We appreciate that. But we've noticed that in between those, there was a huge gap. If you think about it logically, the driver that is overseeing the performance of that vehicle, he will not allow for dangerous situations to happen, or preferably not allow for dangerous situations to happen. He will not put himself nor other people in the traffic at risk. So how do you even with this approach test against those rare and dangerous conditions? How do you test the behavior of a vehicle in a near accident situation? So that creates a massive gap. So what we've been forced to do is to look at the problem outside of the box. We've kind of filled the gap of component level testing, so software in the loop. We've kind of cracked on-road testing. We have our Drive platform, as I've discussed. We have our Hyperion system, which is the infrastructure that collects the data and allows you to instrument your vehicle, but there was a clear gap in the middle. So there was a clear gap in terms of hardware in the loop testing, and this is what our Pegasus system is not Pegasus. Hardware in the loop system is DriveSim is trying to address. Effectively, that system is composed of two devices. One is a server enclosure with the in-vehicle hardware component deployed into that hardware enclosure, and all of the in-vehicle interfaces being taken out of the server enclosure. And the second one is a server which is responsible for photorealistic simulation. So from the perspective of that hardware solution, it is operating within a real car, and that simulation software is providing the real world. And if there is one thing that we're good at, it's computer graphics. Yes, so that's actually something that we've been working on for a while, and something that we very recently released to the public. It's an open utility. Actually, we're not developing it ourselves. We're working with extremely wide range of partners because it's not enough to build a simulator. You need to build an environment model for the entire planet, preferably. You need to build a traffic model, and those models will vary from one geography to another because drivers in the UK, I can assure you, behave differently than those in Spain or in India. You need to build a vehicle model, and there are quite a few of those. They have different dynamics, different masses, different properties on the road, different sensor models, because every single manufacturer will orchestrate, equip their vehicles in a different way, and a scenario model. So you need to define those accidents. You need to create a database of every single thing that can go wrong. Define it in code, and that's non-trivial. But in the end, the results are fairly breathtaking. We can now create extremely highly detailed environments. So those are not video frames from our data capture. This is actually what the simulator will generate. And because it's simulated, you can change it. So you can take that simulated world and change its properties. So you can change the time of the day. You can change the weather conditions. You can adapt the volume of traffic. And as a consequence, you can engineer all of those conditions in which your car can fail and that you need to test against. And as a consequence, you get a very robust utility for regression testing. So suddenly, you make a change to your model, and you can go back and test against every single possible failure mode that then occur. You can change things such as weather as well. And you can deploy it at mass in a data center. It's an open platform. We don't do it alone. We work with an extremely wide ecosystem of solution. It's extremely scalable, and it's available to literally everyone. If you want one, you need to buy it, but you can get one. So it's accessible to OEMs and researchers around the world. And more importantly, we didn't work on it in isolation. We've engaged all of the organizations responsible for safety, and it follows all of the best practices for automotive validation. So that's just a list of companies that we're working with in mapping, companies such as here, OpenDrive, TomTom, 3D mapping and vehicle dynamics, CarSim, IPG, in environmental modeling, 51VR, in system integration, DSpace, companies like DSpace, and sensor modeling, Velodyne and Sony, in scenario modeling, Cognata, and traffic modeling, and Cognata, and more importantly, third-party certification agencies. So agencies that will actually assess the safety of those systems. Yep. And we're working with all of the ones that matter. So companies such as, organizations such as NHTSA, TÜV SÜD, and Euro NCAP. So yes, that is why the problem is difficult. Mm-hmm.
You've said about the simulated
Yep.
model that you're validating on, but you're increasing the number of vehicles.
Yep.
So these vehicles have to be controlled by some kind of AI. So you're validating, assuming all of the cars are controlled by AI.
No, we have a traffic model.
So how does it work?
So we have a set of assumptions about how the traffic will form itself, and then you as a programmer, so a person that is defining the individual test scenario, will define the behavior of individual vehicles. So if you want to have a dangerous behavior of another driver, you'll actually program the trajectory of that vehicle. Yeah. So it's a fairly painstaking, labor-intensive process, but that's the way it needs to be. Yep.
In one of the slides, you said that you have to multiply and accumulate a bunch of numbers. I'm just wondering, are those numbers float 16s or float 32?
So the way we achieve such high level of acceleration is effectively within our latest generations of GPUs, we have built-in hardware acceleration for matrix multiplication. So we have a dedicated part of the silicon that is responsible exclusively for matrix multiplication, and in Volta generation GPUs, that matrix multiplication is done in 16-bit, and in Turing generation, it's either in 16, 8, or 4-bit. We highly recommend to do majority of the training in 16-bit because it's fairly easy, especially for computer vision neural networks. And we recommend majority of inference to be executed at either 16 or 8-bit. 4-bit inference is still fairly challenging, but you can achieve 8 and 16-bit inference almost automatically by using tools such as, again, our freely available TensorRT utility, which will take a model developed in almost any deep learning framework and transform it into a binary that you can deploy to a GPU, and it will do that downscaling of the precision for you automatically.
More questions? Yeah. So,
No, so we'll start with you and then we'll go to the back. I just wanted to acknowledge the fact that I've noticed you.
So we talked about the huge supercomputer that are needed to train the models.
Yep.
So what is the requirement for inference time? Do you deploy that on the embedded machine in the car?
Of course.
Yeah.
Yeah, that's where we've started. We have those non-functional requirements. Latency matters because you need to start braking quite quickly. So that constrains the sizes of the models you can use.
You mentioned there were around 20 neural networks
Yep.
performing perceptive functions.
Yep. Sometimes with overlapping responsibility.
Is there a hierarchy to those, analogous to sort of higher level cognitive functions in
No.
the human brain that
No.
integrates what happens, or they interact with each other?
They very much deliver distinct features that are required to build the solution. Some of them they have deliberately, they serve almost identical purpose, and that's because we want a level of redundancy. So they will achieve same function but in a totally different way. So like, you know, perception of free space versus object detection, they overlap in responsibility, and that's in order to have a level of redundancy. So you have redundancy both in hardware but also in software.
So, perhaps I can pick up
Hmm?
on that point, Nick,
Mhm.
saying that if you've got 20 more or less independent
Neural networks.
neural networks, but then to have a solution, you have to somehow integrate those
Indeed.
results of that.
Yep, and make decisions about driving.
So how does that happen?
So our approach is actually in the public domain. It's called NVIDIA Safety Force Field, and you can download the white paper from the internet. We've been working for quite some time now on a formal approach that we can provide hard warranties of safety to the driver. And that approach uses the understanding of the world to make optimal decisions about the path and trajectory.
Does it use some kind of hierarchy, or is there an ordering? Or
It's deliberately a very simple model so that we can control how it does and what it does. And we actually have also a neural network-based model which is augmenting it and again provides a level of redundancy. But again, it's fairly involved, but the details are published in the Safety Force Field white paper. You can just download it.
more questions?
Are we still at this point, are we still considering neural networks as black box, or are we?
Neural networks are not a black box at all. Why would you say that they are a black box?
I mean,
We know exactly what they are doing.
yeah, but so when a decision is made, or how do the neural network, is there a sense, you were talking about redundancy, but for example, could you point to me an area of the neural network that is, I don't know, dedicated to recognize a pedestrian, for example? Or is it?
I can print you out the logic involved. Whether you would be able to read it, I don't know.
Yeah,
But-
I think there's a good question there, which is that certainly historically neural networks didn't have any introspection function.
Mhm.
It would give you an answer. Is this your question?
Yeah,
It would
exactly.
give you an answer and you didn't know why.
Yep.
And it couldn't explain to you why.
They could. You can print out exact activations on all of the neurons and read that, if that's of any value to you.
That's not
No,
something
it's
that's easy to understand.
So is 200-line long if statement. Yes.
But for example, could you imagine, because so it's an extremely complex environment.
Indeed, hence the testing.
Yeah, but you could imagine that you would be able to isolate, I don't know, a bit that recognize a pedestrian and saying this training is better for pedestrians based on my observation of the neural network, and this
Yep.
other is better
Yeah.
for cars, I don't know.
We do it through systematic test. So similarly, like in software development, where you do not ensure software quality by reading through billions of lines of code, but you write unit tests. Yes, here we rely on extensive testing to ensure that we have robust solution. Yeah.
I think there's a practical
Mhm.
way to frame that question, which is
Mhm.
supposing you were doing validation of a system in a real environment, and you said, it did the wrong thing because it failed to perceive this particular
Mhm.
element. How would you pin that down? How would you get the feedback that the system could tell? You could find out which thing the system did not perceive.
So it's an extremely a wide area of research, and there are quite a few different ways of doing it. It's just you need to watch out about using tools like that, because the fact that you will interpret behavior of that neural network on a single image doesn't mean anything. It's a very complex system. Yes, it's not really informative.
Right, but we've all heard lots of stories about neural networks failing to perceive things.
But we also heard a lot of stories about code being hacked because the developers neglected their duty to do tests.
True,
Yep.
but I think it's still interesting to ask the question, how would you,
Mhm.
I mean, how do you debug it? How do you find out what element of the total set of perceptions
So you know which one failed because you physically have the validation data set and you know on what families of images it is failing. Also, you can design those models in a way where they can give you an approximation of their confidence level in certain types of information. And this is effectively what we use right now to drive both our data collection as well as data labeling campaigns. So it turns out that there is this family of approaches called active learning that you can use in order to get information from the model about the extent to which it's confident in its prediction. So as you drive along, you have no capability to label all of the data, but you use the insight provided by the model to understand where it feels, at which parts it feels confused, and you would prioritize the labeling of those data sets. You would use those data sets to try to formulate additional tests, and then you would hopefully get feedback by addressing those types of problems. There are also quite a few approaches through which you can try to understand so-called local behavior of a neural network, because effectively the only thing that this network is doing is trying to approximate an extremely large function. And so there is if you really want it, you could draw it. Just drawing something in 10 billion dimensions is not practical, but if you have a point, yes, you can piecewise linearly approximate the shape of the boundary within its region. And this is what people do very frequently to try to understand challenges in terms of their behavior. Or what people do is there are really a lot of approaches, but one of the most interesting that I've seen is people will use so-called teacher-student approach, where the neural network becomes a teacher and it's trained on all of the data, and then it's training another simpler model to approximate its own boundary. Then you can use the simpler model to understand the local behavior of the neural network. Or people use attention models to try to highlight within the model parts at which the model focused on and at which it didn't. So there is a huge array of approaches to do it. How useful that is in the grand scheme of things, I don't know. From my perspective, having systematic tests is much more insightful and valuable.
What about adversarial attacks? So when you do adversarial training on network, it's the way you effectively train networks together. One is trying to
Tests.
fail the other.
Tests. Just tests and even more tests.
Okay, but if you don't care for this case, what I've read once is people have found the adversarial attack. That's where you can do a slight modification to your data, and then it completely fails.
But we're talking about a vehicle that is traveling at a speed. You don't have any means of modifying the data. You can also do an adversarial attack on a car right now. You can take a stone and hit the driver through the windscreen, but we don't allow people to vandalize road signs. We don't allow people to vandalize the road infrastructure. So yes, it's a very important area of research, and a lot of companies, including automotive, are investigating those problems. I'm not sure how important of a problem it is within this particular context.
I mean, by using a simulation of the environment and testing the system against that simulation, that is a kind of adversarial
Attack,
testing.
yeah, indeed.
The question will be obviously how comprehensive is
It
the
is.
environment simulation, and does it include what you mentioned as the
And that's one of the main things that automotive manufacturers are doing. They are working with local police departments. They are analyzing the databases of accidents. They are trying to understand all possible situations that led to any problems of traffic. Companies such as 5AI, they are buying CCTV footage from Transport of London to try to understand the structure of the traffic. People go huge lengths to try to make sure that those models are robust. Bear in mind, in this case, you cannot execute an adversarial attack. Yes, you cannot modify the image unless you print a massive sign.
Well, but that's what people have done. I've seen things like people have found the adversarial picture to stick to a stop sign.
Yep.
It's a little sticker, and the system cannot detect the stop sign as a consequence.
Yeah, but then you have to ask yourself to what extent did the author of that system validate that model? Like really, your model is not robust to a dirt on a road sign.
Exactly.
It needs to be robust to a dirt, so that's just not enough testing.
I mean, I think that's a valid point, because if people are sticking stickers over stop signs, then people will be able to see them
But that's a property of small models and small data sets. Yes, we're talking about dramatically larger training data sets, and which are much more robustly tested. Yes, but again, it's a responsibility of all of the automotive manufacturers to address all of those corner use cases. So they should have in their kind of list of all of the things that can go wrong. So in a failure mode sheet, and a failure mode saying that someone will deliberately manipulate with the structure of the road signs, and then they will break it down into all possible things that they can do to that road sign, and they'll iterate that over all possible road signs, and they will have a test against each and every one of those failure modes. This is how automotive validation is done for I don't know how many decades now. So this is effectively how they'll do it. They'll decompose it into small pieces, and they'll test against each and every one of those. Yeah.
Do we have any more questions?
Just a question about the
Mhm.
environment.
Yep.
Before developing neural networks, did you develop your own machine learning environment, platform, special platform?
So we do have a library for classical machine learning. It's called Rapids. For those of you that know kind of the current ecosystem of machine learning utilities and recognize libraries such as Pandas, NumPy, Scikit-learn, XGBoost, we effectively have a drop-in replacement for those, which is GPU accelerated. And when you replace your code with our framework, you should see at least an order of magnitude of acceleration, if not more. So do consider it. But yes, we do.
So I think we're going to ask one last question,
Mhm.
which is, what's a realistic expectation?
That's not a question for me.
See a self-driving car.
You need to invite someone from Volkswagen or
So
that's
you've
not.
got a question you can answer.
No, that's not because it's not up to me.
Which country do you think it will happen in first?
I have no clue. I can tell you where the most money is. The most money unquestionably is in the United States and in China. So, and money kind of helps.
That usually helps.
Yes.
Okay, well, I think this was an absolutely fascinating talk.
Mm.
I think we've got to thank Adam
Thank you kindly.
for giving us a very detailed insight, and certainly having looked at neural networks, 20 years ago when I was teaching, I can see a vast difference in what's being achieved here and in the approaches to. So I think it was completely fascinating, and
Mhm.
thank you very much. Adam.
Pleasure.
We owe you a and there should be food outside the door.
Yep.
Oh yes, and we've got one more thing to do, which is we are going to take you back to the very origins of computing.
Thank you kindly.
With a little gift.
Thank you
And
kindly.
This will teach you about some of the very simple systems.
Our latest generation of GPUs is
It
actually
seemed so simple at the time they were being built.
our latest generation of GPUs. Not by coincidence, is called Turing.
Correct.